So the topic pressure exerted by the liquid. We'll take three scenarios and I will solve by using the numbers so you will have a better understanding. Example, the container is there, which is filled with the fluid. And this container is at rest. Okay. Or it can be a constant speed because when object is at rest or a constant speed, there's no resultant force act. Now, example, the weight of the liquid is 2 Newton. The gravitational pull with this object experience, that is 2 Newtons. So, what should be the downward force in this example? The downward force is because of the weight only. So, the downward force is 2 Newtons. So, if the downward force is 2 Newton, what will be the normal contact force? The normal contact force is also 2 Newton. And if you want to calculate the pressure, pressure is force over area. Let's take base areas as well. Like let's take a base area of 2 meters square. So when we calculate the pressure exerted, we take the downward force. So the downward force is 2 Newton. So 2 Newton divided by the base area of 2 meters square. So what we get? We get the pressure as 1 Pascal. That is the first example in which it was stationary or it was moving at a constant speed. So when it is stationary or constant speed, it does not have a resultant force. The second scenario, that's the first thing. Now, let's take this part. If it is accelerating upward. So we have the same container filled with the same amount of the fluid. And it is accelerating up. So the weight is acting downward, which is already 2 Newton. Now, because as we know, according to Newton's first law, the object tends to resist the change. If this is accelerating upward, what this liquid will try to do to resist the change? What it will try to do? It will try to exert a force. And which direction it will try to exert a force? So as a result, the liquid will apply an additional force, example 1 Newton. So what is the total downward force? Weight is already 2 Newton and the total downward force is additional 1 Newton. So the total downward force is 3 Newton. So the normal contact force on the fluid will be 3 Newton. So what actually happened as the total downward force has increased? So pressure is force over area. Now the total downward force is 3 Newtons and the area is 2 meters square. So what will happen to the pressure? The pressure will be 1.5 Pascal or 1.5 Newton per meter square. So what actually happened is that because it is accelerating upward, to resist the change, the liquid will apply an additional force or a downward force, which increases the total downward force. And as a result of a total downward force, like increase in total downward force, the pressure exerted by the liquid at the same depth will also increase. Is it clear, this example? And the last example is if it is accelerating down, the same amount of the liquid, say a weight of a liquid is 2 Newtons and it is accelerating down. So if it is accelerating down, what the fluid will try to do? Which direction it will try to apply a force to oppose the motion because of its inertia? So the fluid will try to oppose the motion. So fluid will apply, like example, 1 Newton upward. So as a result, what is the total downward force? The total downward force is 1 Newton and the normal contact force will also be 1 Newton. So what about the pressure? Pressure is force over area. So the force, resultant force, like downward force is 1 and the area was 2. So as a result, the pressure will be 0.5 Pascal. So when the lift is, the container is accelerating down, how it become 1? A force of 2 Newton is a weight, and because it is accelerating down, so as a result, what will happen? The fluid will apply a force to oppose the motion, to resist the change in state, or to remain in inertia. So the fluid will apply, example, 1 Newton up. So what is the total downward force? 2 Newton down and 1 Newton up. So what is the total downward force? The total downward force is 1 Newton. So if the total downward force will decrease, the pressure exerted by the liquid will also decrease, even though the depth remain the same. So pressure exerted by the liquid at a constant depth can vary if the object is accelerating up, or a container is accelerating up, or it is accelerating down. Is it clear? Any doubt in this? Okay. Now example 7.5, a copper block of a mass 0.5 kilogram is hung of a thread and put into a water. The density of a copper is 9,000 or 9 exponent 3. So the density is 9 exponent 3. The density of a water is 1 exponent 3. Calculate the tension. So first we have to draw a diagram for this. Say this is a water, and object is there, a block is there, is hung by a thread which is inside. So the copper is there inside. We want to calculate the tension, T. Now, if we want to calculate the tension, we have to identify what are the forces acting on this. So what are the forces acting on this? First thing, the weight of this block, which is acting downward. Another thing, because the object is in the liquid, so there will be an upthrust, which is acting upward. And another force, the tension, which is also acting up. And because it is inside the water and it is at the constant position, so we means what should be the resultant force? The resultant force is 0. So if the resultant force is 0, I can say tension plus the upthrust is equals to weight. Is it clear? Or I can also say tension plus upthrust minus the weight is equals to 0. Both are the same things. So I can write tension plus upthrust equals to weight, or I can also write that tension plus upthrust minus weight is equals to 0. So both statements are correct. Now what about the tension? We because in the question we want tension. So tension is weight minus the upthrust. How to work out the weight? Weight is mass multiplied by gravity. So if we want to calculate the weight, we can work out the weight, which is mass into gravity. The mass is 0.5 and the gravity is 9.8. So 0.5 multiplied by 9.8. That will give us the weight of this block, which is 4.9 Newton. How to work out the upthrust? 4.905 or 4.9. How to work out the upthrust? Upthrust is the density of the fluid, the volume of the displaced fluid, and gravity. Whenever object is completely submerged, it means the volume of this volume is the volume of object. So how to work out the volume of object? We have the mass and we have the density, so we can work out the volume of object. Volume of object, because density is mass over volume, so volume is mass divided by density. So mass is 0.5 and the density of the copper is 9,000 or 9 exponent 3. So 0.5 divided by 9,000, it will be 5.5 into 10 to the power negative 5 meter cube. So we got this volume of a displaced liquid, because the volume of a displaced liquid is same as the volume of object when it is completely submerged. Density of the water is given to us, which is 1000. So how much is the upthrust? The density of a water 1000 multiplied by the volume of object, which is volume of displaced liquid, which is 5.5 into 10 to the power negative 5, and into gravity 9.81. So how much is the upthrust here? What is the upthrust? 1 exponent 5 multiplied by 5.5, 0.54. Okay. So we got 0.54. 0.539. So we can round off to 3 significant. And so tension will be weight minus the upthrust. In this example, so weight is 4.9 and the upthrust we work out 0.54. So the tension in the string will be 4.9 minus 0.54, which is 4.36, 4.46 or 4.36 Newton. Yeah. So that is the tension in this. Is it clear? Anyone having a doubt in this example? Okay. Next example, you have an ice cube of size 2 centimeter floats in a cup of a tea. One of its face is 0.2 centimeter above the surface. A ice cube is there of a size 2 centimeter, and one of its faces is 0.2 centimeter above the surface of a tea. Calculate the density of the tea if the density of the ice is 920 kilogram per meter cube. So how we can solve this? So when the object is whenever object is floating, what we can say? We can say that how much the upthrust is equals to weight of a liquid displaced. So upthrust is equals to the weight of a displaced liquid So we can say the upthrust is equals to how much liquid is being displaced, that we can write. Or we can also say because it is floating, when object float, so the weight which is acting downward, the weight which is acting downward will be equals to upthrust when object is floating. And upthrust is equals to weight of a liquid displaced. How much liquid is being displaced by the object, that is equals to upthrust. So the statement which we can write here, the first statement we can write that the weight of the object is equals to the upthrust. That is the first thing. As it is floating. What about the weight? Weight of an object? Weight is mass into gravity. Mass of ice into gravity. And what about the upthrust? How we can say weight of an object is upthrust? Because it floats. When object float on the surface, the weight which is acting down means there is no resultant force. So weight must be equals to upthrust. Otherwise, if the weight was greater, then it will sink. So minimum we take that the weight should be equals to upthrust so that it will float. So weight is equals to mass into gravity or the mass of the ice into gravity. And what about the upthrust? Upthrust is a density of the fluid, means the density of a T. What if the upthrust is greater? If the upthrust is greater, it should rise up, like it should not, but it cannot leave the surface at there is a surface tension. There is another force which is a surface tension that does not allow the object to leave the surface. So minimum, whenever we are solving a question related to the floating, we assume that the weight is equal to upthrust. Upthrust can be more than the weight. In that case, the object should rise. If the object is released here, it will rise when the upthrust is more than the weight. At this point, if the upthrust is more than the weight, then the object should leave the surface. But there is another force which is the surface tension that keeps the object in contact with the liquid surface, does not allow to escape. So upthrust is equals to density of the T, because T is the fluid, volume of the displaced T into gravity. Is it clear till this point? Upthrust is equals to density into volume of a displaced T. Like how much this T will be displaced, that is the volume. So when we just need the volume of this part, because this is a part of the cube which is inside the T, and that is how to work out this volume. The sides are 2 centimeter. So what are the dimensions here? Like what is the volume of this part? 2 multiplied by 2 multiplied by 1.8. Is it clear? That how much T will be displaced by this? Because two of the sides are 2, but one of the side is 1.8. So this is the volume of the T which is displaced. 2 multiplied by 2 multiplied by 1.8. And then, so 2 multiplied by, like it will be 3.6 into, so that is 7.2 centimeter cube. But because the density is given in meter cube, so we have to convert the centimeter cube into meter cube. If you want to convert the centimeter into meter, we divide it by 100. But centimeter cube to meter cube, we divide it by 100 cube or 1 million. So that is equals to 7.2 into 10 power minus 6 meter cube. So we got this. What about the mass of the ice? We don't know the mass of the ice as it's not given. So we can also change this formula that mass is density into volume. So the density of the ice, volume of the ice into gravity will be equals to density of the T, volume of the T which is displaced into gravity. What about the volume of the ice? The total volume of the ice, each side is 2 centimeter. So it will be 2 multiplied by 2 multiplied by 2, which is 8 centimeter cube. But when we convert into meter cube, to convert centimeter into meter, we divide it by 100. But centimeter cube to meter cube, we divide it by 100 cube. So this will become 8 into 10 power minus 6. Now, because our objective is to find the density of the T, we just substitute the density of the ice was given the density of the ice was 920. So we write here 920 like this formula. Volume is 8 into 10 power minus 6. The volume of the ice multiplied by gravity 9.8. The volume of the density of the T we don't know. The volume of the T which is displaced, that is 7.2 into 10 power minus 6 multiplied by 9.81. So we just simplify, make subject as a density of the T. What's the final answer for the density of the T? What's the final answer for the density of the T? It's, yeah, 1022, right? That's right. Or in exponent, I can write 1.02 into 10 power 3 kilogram per meter cube. Is it clear? Discussion? So whenever object is floating, you will always assume weight is equals to upthrust. And if the object is completely submerged, that case the volume of object is same as the volume of displaced fluid. But how much object is inside, like if it is not completely submerged, then only the volume of a displaced fluid is only the part which is inside the fluid. Is it clear? Anyone having a doubt or a question? So example, a long solid cylinder is hung vertically from a spring balance. As you can see here, this is hung from a spring balance and it is on the compression balance. This is a compression balance. How compression balance work? Like how much you compress them. Compression balance, the best example, like we used to find our mass, we stand on that balance. We call that as a compression balance because how much it is compressed, that shows the deflection. And the spring balance use extension. How much the spring extend, that will shows the reading. So a long cylinder is hung vertically from a spring with a spring balance with a base of a cylinder few centimeter above. The cylinder is then slowly lowered into a water until it is several centimeter below the water. On the diagram, how the reading of a balance changes when the cylinder is lowered. So if we lower this cylinder, how the reading of the balance will change, that we have to find. Like how the reading of the spring balance will change and how the reading of the compression balance will change. Look, what about the reading of the spring balance? When the object is inside, so what happened to the reading of the spring balance? Will it increase or decrease? So when we just take the spring balance, you have a container which is filled with the fluid. And there's an object which is submerged. And you have the spring balance attached to that. So how the reading of the spring balance will change? Like example, if you take when it is outside, what are the forces which are acting? One is the weight of the object acting downward. Another one is a tension. Because whenever force applied by using a string or a wire, we call that as a tension. So there's a tension. But when it is submerged, then what are the forces which are acting? The weight is acting downward. The tension is acting upward. And there's also another force because the fluid will apply an upward force or upthrust. So it means the tension plus the upthrust is equals to weight. Or tension is equals to weight minus the upthrust. So tension is equals to weight minus the upthrust. What does it mean? It means the reading on the balance will decrease. So the reading of the spring balance will decrease. Is it clear? Because here the tension was equals to weight, but now the tension is weight minus the upthrust. So when you subtract, you get a smaller value. Your weight will remain same, but there is an upward additional upthrust is there. As a result, the total tension to pull the object will decrease. Weight will not change. It shows reading of a tension, not the weight. The spring balance is actually showing the downward force. So actually what happened, how the tension decreases because the downward force decreases. If I use the number, say it was 10 Newton here, so the tension is 10 Newton. Weight is 10 Newton, but example, the upthrust is 2 Newton. So how much tension should be there to balance that? As it is stationary, to balance that, how much tension should be there? So the tension will be 8 Newton. So tension has decreased because upthrust is helping the tension to balance the weight. That is why when you try to lift heavy objects underwater, you will find it very easy to lift. For example, you want to lift a weight of, say, 50 kilogram underwater, you will find it much more easy as compared to that in air. Because the water also help you apply an upward force which make the upward force less. So the tension will decrease here. Or the reading on the balance will decrease. Is it clear? Any doubt in this? The second thing is the compression balance. So if it is on the compression balance, first, the weight of the liquid was acting downward. Okay. So the compression balance, the normal contact force, the compression balance is there upward, that is balancing. But then what happened when the object is submerged? Now it is placed on the compression balance. So what will happen to the reading of the compression balance? The reading of the compression balance will change. It will increase. Why it will increase? Because initially the weight of the liquid was there. Initially the weight of the liquid was there, that was acting downward. So the compression balance apply an upward force and that shows the reading. Or we can say R is equals to weight of the liquid. But then what happened when object is submerged? So there is a weight of the object plus the weight of the liquid. So what will be the upward force from the compression balance? R. So the total downward force increase. So R will be equals to weight of the object plus the weight of the liquid. So what will happen to the value of R? R will increase. So means the total downward force has also increased. So the reading of the compression balance will increase, but the reading of the spring balance will decrease. And how much increase is there in the reading of a spring balance? How much decrease is there in the reading of a spring balance? Same amount of increase is there in the reading of a compression balance. If, like example, the spring balance reading decreased by 2, the compression balance reading increased by 2. Is it clear, this example? So shouldn't it, because the upward upthrust exerted by the liquid on the object is an extra opposite downward? Why does the R include? It can be weight of an object that is connected with a string. Yeah, Imad, look, I got your question. I got your point, what you mean. So actually what is happening? Yeah, it's the same idea, same concept. That's why I said how much increase in the value of the reading, that same amount of the reading will decrease for the, like for a spring balance, how much it decreased? the same amount will increase for the compression balance. So it depends on the frame of the reference which you are considering. What I consider a container, I'm considering water and this object as one. Okay. So what is the total downward force? One is the downward force of the liquid. Another one is the downward force of an object. If the total downward force increases, what will happen to the reading of the compression balance? The reading of the compression balance will also increase. But when I was considering a spring balance, we don't have to include the water in that case. We just have to consider the forces which are acting. So an object is there in the fluid. And the forces which are acting, one is the weight of an object. Like right now, because when I'm considering the spring balance, I did not include the weight of the liquid. So the weight which is weight of the object is acting downward, and because object is in contact with the liquid, so liquid is applying an upward force, upthrust. So in that case, the total up, because the total resultant force, and there's also a spring is pulling this upward, so tension is there. So in that case, the tension and the upthrust are acting upward, where weight is acting downward. So the tension is equals to weight minus the upthrust. So means how much the tension decrease, the same like how much value of the compression balance increase, the same amount of the value will decrease for the spring balance. Is it clear? And you can also answer this in terms of the, you can also answer this in terms of the upthrust as well. It won't make difference. You can answer this in terms of, like, for example, if I want to answer in terms of the compression balance is there, in terms of the upthrust, so a container filled with a fluid and there's an object. So the what are the forces acting? One is the weight is which is acting downward, weight of a liquid. Another one is the weight of an object which is also acting downward. So what is the total downward force? So the total downward force is the weight of the liquid plus the weight of an object. And according to Newton pair force, so if the total, like the total downward force is there, which is the weight of a liquid plus weight of object, then there will be a total upward force, R will be there. R is a normal contact force. So the normal contact force or R will also increase. And so I can say R is equals to weight of a liquid plus the weight of object. Is it clear? An object is attached. Is it clear till this point? Anyone having a doubt or a question? No, it depends on the frame of the reference, what frame of the reference you're considering. Because the total when we are talking about the normal contact force, when we talk about the normal contact force, we are only considering what is the total downward force. So one is the weight of the liquid, another one is the weight of object. That is the total downward force. So the total downward force balances with R. R is a reaction force on the liquid by the surface. So total downward force balances with the R. So we can say R is equals to the weight of the liquid plus the weight of object. This is a scenario when the object was not attached with a string, like object was floating. But if there is an object which is like hung by a spring or a string, so there is another upward force is there, tension. And if I want to write the statement now, so if I want to write the statement now when there's a tension, so what should be the equation? R plus T is equals to weight of a liquid plus weight of the object. Now that will be the equation we will use. So two different scenarios. This is a scenario when the object is floating without a string. And this is a scenario when the object is floating with a string. So if it is floating without a string, I will write that the total downward force is equals to weight of the string, weight of the fluid plus weight of object. But if it is attached with a string, there is a tension force acting upward. In that case, R plus T will be equals to WL, like weight of a liquid plus weight of object. Is it clear, Ahmad, your question? Is it clear? The conditions in which we draw? So today's topic was density, pressure, and the upthrust. No, we don't have to add upthrust because upthrust is only the force we already worked out. We don't have to add upthrust because what actually happen is when object is there in a fluid, the spring will pull. That is the tension, the resultant of these two, weight and the upthrust. That is T. The surface, the normal contact forces there are the weight of a liquid is acting downward and the weight of object is acting downward. So in that case, the R, the reaction force plus the upward force of the spring will be balanced with the liquid, weight of the liquid and the weight of object. Why we did not consider the upthrust here? Because this upthrust and weight, the combination will give us the tension. So tension is actually the result of these two. The weight of object and upthrust result is the tension. That's why we did not include that. Is it clear? Any question or doubt related to the session today? So about the Newton law doubts, I have already recorded the session for that. So I will share that recording, go through the recordings. If you don't understand any part, you can ask in the next session. So I'll end the session and share the related recording. So weekly homework is already shared with you about the motion. You just solve that and submit today.